So it's my pleasure to talk a little bit about energy. And here on this slide, I'm showing some of what we have grown accustomed to is the idea of large-scale solar panels that are actually producing quite a bit of energy. And let me show you a slide from Germany. And it shows the amount of solar generation that occurred back in May of this year. And what you have is a remarkable sight is that half the electrical energy in the entire nation of Germany was actually being produced by these types of solar panels. And this is an indication of the tremendous commitment and subsidies in Germany, but we need to obviously make further improvements in order to go further. So let me describe to you some work that was done with a graduate student here at Berkeley, and it's Owen Miller, who graduated in May of this year. And we have sort of changed the rules of solar cells and have broken the record of solar cell efficiency. And so I'll describe the old picture of solar cells. Is light came in and you produced an electron hole and you collected them and you got electricity. Okay, and let me show you the new picture. In the new picture, the light comes in and doesn't always go directly to electricity. First, it goes to infrared radiation. And the infrared radiation bounces around inside the solar cell. Some of it escapes. And you end up with the remarkable situation that you might have one sun coming in, but you trap internally 40 or 50 suns of infrared radiation. And this becomes then a requirement for achieving the new efficiency records. So the efficiency in the past couple of years has gone from 25% to very close to 29%, and soon it'll be 30% efficiency. But I have to tell you that it didn't come automatically. Of course, Owen did his research and he figured out the theory, but until we started seeing some experimental results come in, we didn't really believe the theory that strongly. And the first indication was the voltage. The voltage was, we were getting a voltage that was way higher than expected. And they were higher than anyone had ever seen before. And we went back and looked at the theory, and of course it was all there. And what the theory says is that in order to achieve these very high voltages, you actually not only do you take the sunlight in, but you have to give some light back. Some of the infrared light has to be given back. And this is extremely counterintuitive. And we got a lot of resistance to our ideas. It says, well, why should a solar cell ever give any of the light back? And yet it's a requirement to achieve the highest efficiencies. And so I think this is something that is just gradually seeping into the field and becoming accepted. But it helps a lot, of course, to have a world record to go along with it, which he does. Now, the question arises how to make these. Of course, now the efficiency looks like it's going to be very high. And, well, we'd like to make them out of gallium arsenide. These are the best solar cells, use them on satellites, but the cost is very, very high. So let me show you how the cost is going to be reduced. And this is by peeling the films off of a substrate and reusing them. And it just so happens I have one here in my pocket. And I'll just show you what it looks like. This is basically the new type of solar cell that has this fantastic efficiency, and it's completely flexible, just like in the picture. And what we envision is that this type of material will actually be covering large tracts of land and be kind of a new type of agriculture, a new way to use land to produce energy. And so that's part of the excitement there. So let me go on to another aspect of energy, and this is something maybe we're all accustomed to, is we click on Google and we get the information we want. And you may have wondered, where does that come from? And it actually comes from a Google data center, and there are other companies as well, of course. And the data centers, well, they're kind of big like this, and from a distance they look a little bit like a power plant. In fact, they're usually adjacent to a power plant because they use so much electricity. And so this is a problem that will continue to create difficulties as we expect more and more from the cloud, from the internet. And you can see that the amount of energy dedicated to data centers has gone up in 2000, 2005, and up to 2010. It's well over 2% of our electricity is going into data centers. And of course, there's the rest of electronics also. So the energy use, the electricity use in electronics is very important. And if you ask, well, where's the energy going? Well, it's going to all these wires. This is sort of a close-up of a chip. And looking inside, like X-ray vision, you see there's all these wires, and most of the chip is consisting of wires. And you're putting a voltage on, and as you put on more voltage, you use more energy. And so the problem is the voltage is too high. If you look at what has happened with the development of the electronics industry, the voltage was going down, 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 and now it has stopped going down very much. And your chips are requiring about 1 volt of electricity. Now, if you look, though, at the requirement, what would a chip really need? You should be able to go down to 1 millivolt. So it looks like we can reduce the voltage by 1,000, and energy goes as voltage squared. And so it looks like it should be possible to make electronic devices, electronic chips, cell phones, you name it, 1,000,000 times more efficient. And so this has turned into a very big research project here at Berkeley. Let me show you the device that is going to replace the transistor. And it's a little hard to explain, but the current comes in here and it jumps across, and you have both, like a normal transistor would have just an N channel and a P channel. Here we have both, and it jumps across by quantum mechanical tunneling. And this looks like it's capable of having much lower energy. It's another picture of the same device. The current would come in, jump across like that. And the secret to making it work as a switch is you have energy levels, and when the energy levels are lined up, the current jumps across. And when they're misaligned, if the energy level is up here, the current would have no place to go. And so this is a new device that we are working on that we just recognized just in this year that looks like it is the best candidate we have for replacing the transistor with a much lower voltage device that would be much more efficient and save us many orders of magnitude in energy. So the National Science Foundation has recognized the importance of this project, and with the leadership of Berkeley, we're leading both MIT and Stanford, and we have a national effort. There are also some international efforts to achieve the same thing. And so I'll just show you the magnitude of the effort. We have a great many professors who are all dedicated to this project. And this type of work is really enabled by the chairs and allowing us at the beginning stages to look at speculative research. But I'd like to close out my discussion with this paradox that I gave you earlier, is how could it be that a solar cell works best when it actually gives back some of the light? This is very counterintuitive. And my student and I have had tremendous difficulty getting people to accept that. But the analogy I'd like to give is with respect to society. And that is that the society works best if people also give back a little bit of what they have. And it's a little bit like how the solar cells become optimized. And they also give back a little bit, and this gives the highest possible output voltage. So.